So superheat subcooling, we've talked about it enough throughout the chapter, but I want to make sure you guys really have a good understanding of it. So I'm going to just talk about it a little bit more. All right, so superheat. The amount of heat added to a refrigerant after it has evaporated on the low side. All right, what does that really mean? Okay, we have refrigerant. All right, it's a saturated vapor state. Saturated vapor state is a refrigerant in vapor form under conditions that would cause some of the vapor to condense if any amount of heat were removed from it or the pressure is increased. So if we have refrigerant that is maintaining a set pressure, all right, we'll just say it's 100 psi, okay? At 100 psi, and we're going to, let's just work with R22, and I'm going to actually pull up the real numbers this time for you guys so you have an idea. R122 at 100 psi is going to maintain a 59-degree temperature. All right, what does that mean? Anything above 59 degrees, that refrigerant is going to be in a vapor state. Anything below 59 degrees, it's going to be in a liquid state. All right, as long as the pressure maintains the same. So what we have to understand is we've got that vapor or that temperature pressure relationship. So as I increase the pressure and I go up to 125 psi, well, now all of a sudden my saturation point is 70 degrees. So anything above 70 degrees is going to be in a vapor state, and anything below 70 degrees is going to be in a liquid state. All right, so superheat. The amount of heat added to a refrigerant after it has evaporated on the low side. So what that means is if my temperature at 122 psi is 70 degrees, anything above that 70 degrees that we measure is going to be what we consider superheat. We're going above our saturation point. So if I have 122 psi, but I have an 80-degree temperature, I've absorbed 10 degrees of heat into our refrigerant. And by doing so, now I have a little bit of a buffer from turning into a liquid from a vapor. All right, so that 10-degree difference is what we're going to consider a superheat. All right, the most common form of superheat, or the majority of ways we're going to charge a system based on superheat is how do I phrase this? I'm sorry. The most common places that you're going to find this occurring, the saturated vapor, is in the evaporator and the condenser. All right, what does that mean? We have a state, all right? We have refrigerant that's traveling through our liquid line, all right? It's coming through, we've got a little TXV here, for example, and what's happening is we have all this liquid refrigerant that's being built up. Remember, our metering device is sort of like a stoplight, and what ends up happening is that stoplight, or our metering device, is going to allow certain amounts of refrigerant to come through. All right, we've got a buildup of high-pressure liquid refrigerant. So that metering device is going to allow just enough refrigerant to come through for it to drop pressure. As that liquid refrigerant starts to travel through, we have a steady stream of air being blown across it. All right, so this is our evaporator. What ends up happening is heat starts to get absorbed into the refrigerant, and it starts to create this change of state, because we've taken our high pressure liquid and we've turned it into a low pressure liquid at its saturation point. So we have that ability to go from either a vapor to a liquid or a liquid to a vapor. But because we're blowing across the evaporator with warm air, that refrigerant is going to want to turn into a vapor and stay in a vapor state, because we're increasing the temperature. All right, that heat is being absorbed into the refrigerant. By doing so, we're going to absorb enough heat so by the time we get to the end of the evaporator where we take our measurement, we'll have a total of 10 degrees of superheat absorbed throughout the evaporation and cooling process right here. Why is that important? All right, it's important because what ends up happening is if I don't have all this heat that's being absorbed here and it's so close to the saturation point, there may be liquid that's still left. All right, we haven't sort of crossed that boundary, and there's the potential of having that liquid into our system. All right, into our compressor. Compressor doesn't like liquid. It's not going to compress it. We're going to have issues, and there's going to be potentially a malfunction. With the little asterisks thrown in there, scroll compressors are a little bit better at being able to pump liquid refrigerant if it happens, but we still don't want it to happen. So we want to make sure that we have that superheat involved. That being said, this drawing is actually incorrect, and I just noticed it now. There's a TXV here, all right? There's still going to be superheat in here, regardless of the operation, but we will actually charge this system via subcooling, all right? Why? Because the superheat level is being determined by the TXV, all right? So the refrigerant is going to be monitored by this device. It's going to open and close based on what the superheat level is here. So if my superheat doesn't achieve a 10 degrees or, if it's lower, it's going to determine that, hey, I have maybe too much refrigerant coming through, and so it's going to close this little needle inside the TXV down. If I have too much of a superheat, well then I'm going to open up inside here and allow more refrigerant to go through. So there's an ever-changing battle between the spring inside the TXV and the diaphragm at the top. All right, so superheat is always going to be on their system no matter what, but charging it is going to fluctuate, all right, depending on the type of metering device that we have. So that's always critical to know, all right? So just an example of superheat and subcooling. Superheat, it's the temperature difference between the refrigerant coming into the evaporator, changing state, and then coming out, all right? So it's just this area that we're really measuring. And why is this important? Well, we want to measure how much heat is being absorbed. The other thing too is when we are hooking up our systems, we're going to notice that there's a line. Our vapor line is going to be covered in insulation once it exits the evaporator, and it runs all the way on over to the condenser. And why is that important? All right, it's important because we have a really cold refrigerant that's traveling through there, and what's going to happen is that pipe, if it were exposed, it's actually going to start to condense. Why? Because we're going to have a refrigeration effect happening outside of the system. We have 55-degree refrigerant, or whatever it is, traveling along this pipe, right? And in this diagram, we're actually running in reverse. So the refrigerant's actually flowing in this direction, going from a dark blue to a light blue. And what happens is we can still absorb heat even though we're not having warm air blow across it in the evaporator. There's still heat that's in the air, all right, that's inside the building. And what happens is if that warm air comes in contact with that 55-degree line or 35-degree line or whatever it is, well, we're going to start to get condensation, all right? We're going to still absorb more heat, all right? More heat's going to want to get into that refrigerant because heat travels to a place that is much cooler, all right? We're removing heat. And that refrigerant is going to start to absorb more heat, more heat, more heat, more heat. And eventually we're going to get to the condenser outside, and we're going to have a 30-degree superheat. And we're going to wonder, well, why? Why do we have 30 degrees? And we're going to adjust our charge, and everything's going to be out of whack because we decided to put more refrigerant in there when it really didn't need it. So we need to make sure that our lines are insulated, all right, from the evaporator all the way over to the compressor. Not only is it going to help prevent additional heat from being entering into our refrigerant system, it's going to help dissipate that heat, all right? We want to target the area here inside the ductwork, inside of our evaporator, rather than trying to absorb heat all along this line, okay?
Hey guys, this is Craig Migliaccio with AC Service Tech, and today what we're going over is how to check the refrigerant charge of a system with a fixed orifice using the total superheat method. Check out our book, The Refrigerant Charging and Service Procedures for Air Conditioning. In this book, we go over the preparation of the system for refrigerant, checking the refrigerant charge, and troubleshooting methods. You can check out the full outline of the book and also purchase the book over at ecservicetech.com. In order to check the refrigerant charge of an air conditioning system, you first have to check to see what type of metering device the system has. Does it have a thermostatic expansion valve, or does it have a piston or capillary tubing? So on this system here, we have a piston, and you can tell that just by the nut right in front of the air handler. So right where the small liquid line enters the lower portion of the air handler, there's a nut right there, and inside that nut there is a piston. So we need to check the refrigerant charge of this system with the total superheat method. If the system had a capillary tubing, once again, you check it with the total superheat method. And if the system had a thermostatic expansion valve, then you would need to check the refrigerant charge using the subcooling method. It's kind of nice checking the refrigerant charge with the subcooling method because you can tell what the target subcooling is just by looking over at the rating plate. It's usually posted right there as the target subcooling or the TXV subcooling. But when you check the refrigerant charge of a system with a fixed orifice such as a piston, you need to use the total superheat method. So, in order to find the target superheat, you need to take two measurements. One is the indoor wet bulb temperature, and the other is the outdoor dry bulb temperature. The indoor wet bulb temperature is measured with a digital psychrometer, and you're measuring that several feet before the evaporator coil. So you're measuring it in the return duct, and if the return grill is very close to the air handler, then you can check the wet bulb temperature there. But if not, we typically drill a small 3/8 hole in the return duct, and then we place the digital psychrometer in that hole in order to check our wet bulb temperature. When you're done, you just plug that hole with a 3/8" duct plug. So anyway, you see that we have a digital psychrometer right in the return there, and it's reading a indoor wet bulb temperature of 68 degrees Fahrenheit. So we're going to take that wet bulb temperature, and then we're also going to look at our outdoor dry bulb temperature. We're going to measure the outdoor standard dry bulb temperature about a foot away from the outdoor condenser coil, which is where the inlet of the airflow is. So we don't want to measure at the top, typically where the air is blowing out very hot. We want to measure our temperature as the incoming air temperature to the outdoor coil. And as you see right here, we're reading 92 degrees. You take that wet bulb and dry bulb temperature, and you can input that onto a target superheat chart, or you can put it onto a calculation or an app, and you could also just...
I'm just going to pause it right there really quick. All right. Why is he going in so in depth right here with dry bulb, wet bulb, that sort of thing? Well, the reason being is under different conditions, we're going to have varying parameters for our system, all right, our operation. So let's just quickly look over at this chart, all right. Outdoor dry bulb temperature, let's just say it's a nice 80-degree day, and our indoor wet bulb temperature is a 70, all right? So our target superheat is gonna be 25. But if I have the same temperature and I have a 60-degree wet bulb, well, I have 8 degrees of superheat. So what does this mean? Why is this important? Well, it's important because if our system was initially started up, all right, and let's just say the home, the air conditioning system was broke down, hasn't operated for a couple of days, it's nice and toasty inside there, we're going to have a lot of heat inside the building, all right? We're going to have a lot of heat that's not only sensible, but it's also going to be latent, all right? So we're going to have this heat that we have to remove. And so the air conditioning system is going to struggle at first because we're trying to remove and we're trying to play catch up. And what ends up happening is, as we start to remove this latent heat and sensible heat out of our home, well, now all of a sudden, we're not going to need the air conditioning system to operate as much and as heavily. And so if we were to maintain that 25-degree superheat, at a lower wet bulb, well, our refrigerant charge is going to be off, all right? We're always trying to maintain this equilibrium, all right? It's just the right amount of refrigerant inside the system so it operates properly based on the conditions. And so what you do is you measure your indoor wet bulb, all right, and you're using a psychrometer. I think we talked about it a little bit ago. There was a sling psychrometer used to spin around, and it would determine how much heat really potential is in the air. And that's what we're doing. All right, we're trying to see how much heat is really still left in the air, the difference from the indoor to the outdoor. it's going to tell you what your recommended superheat is based on the conditions. All right, so you've got this chart, and depending on what your conditions are, you're going to charge the system based on that. One cool app to have instead of having this chart, it's called Emerson's check-in charge. Really cool setup. Various amounts of refrigerant out there. You can do superheat, you can do subcooling. Real simple to use. I'll show you guys that at the end here what it looks like, but good stuff. All right, so it basically points out this whole chart, makes it real simple for the technician when they're out in the field to dial in the system properly. Otherwise, what will happen is if I were to overcharge the system, well, now I'm going to have too much refrigerant in there. It's not going to properly remove the heat as needed because I'm going to have an influx of liquid, and liquid's not doing the work, all right? It's that saturation point where we're going from a liquid to a vapor and then absorbing extra heat in that vapor state, okay?
Use the measurement on the digital manifold gauge set. But in this instance, we're going to be using the target superheat chart. So if you look at 68 over at the top, and you bring that down and you're lining up with 90 degrees, you have a target superheat of 16 degrees. Now, right below that, you see if our outdoor dry bulb temperature was 95 degrees, it would be 14. So we're looking at right around 15 degrees as a target superheat. When we connect the refrigerant manifold gauge set, we take the red hose and we connect that to the small liquid line, and that's going to connect to our red high side gauge. Our blue hose connects to our large vapor line, and that connects to the blue low side vapor gauge. For the total superheat, we're going to need to measure our vapor line temperature within 3 inches. So you see that we have our temperature reader at T2, and we have a clamp on the large vapor line. It's also important to note that the tubing needs to be clean if we were going to use a temperature clamp. You can also use a bead-type temp sensor, and that you'd have to tape onto that large vapor line.
So the other cool thing about this illustration is you guys see how this vapor line, the blue line right here that he's going to be connected to, is all insulated. All right, it's all insulated going all the way outside to the condenser. All right, we don't want to absorb any additional heat because that's going to throw our system off. The other thing too is if you were to go ahead and take this thermal probe and actually attach it right outside the evaporator, you're going to get a more precise reading, all right, because we're taking the temperature exactly as it's coming out from doing the work. We may absorb another degree or two as it travels down through the insulated line, but from a convenience standpoint, a lot of times we're just going to be grabbing the temperature right outside of the vapor line. All right, our gauges, everything is outside there. It's usually pretty close to where we need it to be from a ballpark standpoint. Maybe talking about a couple of degrees with the insulated line, but so you're going to be more accurate measuring here. Okay.
So once again, that needs to be within 3 inches of that surface port in order to compare your pressure and also your temperature at that location. One more thing that you want to make sure of is that the gauge set handles are shut. So before you even turn that system on, you want to have that manifold gauge set connected, your handle shut, and then you can go ahead and turn the outdoor air conditioning unit on. So before you turn the air conditioning system on and try to check the refrigerant charge, you want to go ahead in the inside of the house and make sure that you check the indoor air filter to make sure that it's clean, and you want to go ahead and check the airflow speed. So what I typically do is I pull the disconnect at the outdoor condensing unit, and then I go inside, check the air filter, and I also check the blower speeds at the control board. And so after that, I turn the indoor system on air conditioning mode, and I let the airflow come out of all the registers, and then I check the airflow at the registers with an anemometer. So this way I'm able to determine if I am blowing the correct amount of airflow across the evaporator coil. It's important to make sure that you have the right airflow at that indoor coil so that the indoor system and the outdoor system are matched. You don't want to have a 3-ton outdoor condenser matched with a 3-ton indoor evaporator coil but only running 2 tons of airflow, so that would not be good. Anyway, once you check the airflow, you make sure that that's good, the air filter is clean, and you go out to the outdoor unit, and then you Go ahead and turn on the electric to the outdoor condenser via that disconnect box right there on the wall. And after that system is turned on, now you're going to be monitoring both the blue gauge and the red gauge. Now remember that our target superheat was right about 15 degrees of target superheat. But it's going to change, and the reason for that is the indoor wet bulb temperature is going to decrease as the system is running, and that's because you're reducing the humidity inside the building. So during the first minutes of runtime, you want to check that vapor saturated temperature on the low side gauge, and on this system right here is the R410A system. So we're checking the pressure on the outer ring, and we're going to bring that pressure into the inner ring. If you see the pink area where it's R410A, and you see that the numbers are in black right there, that's going to be the saturated temperature of R410A at the indoor coil. So we first need to make sure that that saturated temperature is above 32 degrees. If it's below 32 degrees, then we have a problem. So you got to give it, say, 3 minutes or so, 3-4 minutes, and that saturated temperature on the low side should be above 32 degrees if there is no problems. If there is a problem, then you may have low airflow at the indoor coil, or you could have a liquid line restriction, or you may be low on refrigerant. You can use our guidelines in the refrigerant charging book.
So why is 32 degrees important? Why is that the magic number? Well, we're dealing with sensible and latent heat. Once our evaporator starts doing its job, all right, it's got that pop can thing going on. We take a cold pop can out of the fridge, we set it onto a countertop in the dead of summer, it's going to start to sweat, all right? As we have our warm air that comes across the evaporator, all right, our evaporator's roughly about 55 degrees, okay? That warm air, 70, 80, 90 degrees, whatever it is, as soon as it hits that, we're going to start releasing that latent heat. We're going to start to get that condensation start to form on our evaporator, and we're going to have water, all right? Water's going to start draining out. If our coil, all right, our evaporator coil is 32 degrees, we are no longer removing water and humidity, all right, dehumidifying the space, but we're now turning everything into ice, all right? 32 degrees is the temperature water freezes, so our air conditioning system now has turned into an ice maker, all right? What ends up happening is once we're in an ice making state, there is no reversing it. That system's going to continue to run, and it's going to continue to keep making ice until it turns into a big frost ball, all right? Once that happens, we can't adjust the temperature, we can't adjust the pressure, we have to let that ice all fully melt. Once it melts, then we're able to come back in, fire up the system, see what's going on. Big disclaimer, if you have an ice ball, anything like that on an evaporator, condenser, lines, all that stuff, don't hit it with the hammer, don't hit it with the screwdriver, don't do any of that stuff. You want to let it melt, all right? If you want to apply a little bit of a heat to it, you can via heat gun, pouring warm water on it. You can have the furnace blow air across it to help just naturally melt, all right? Whatever it takes, but by no means don't use any type of physical force to try to do that, because you may rupture one of the lines, all right? If you rupture one of the lines, you're going to have issues, all right? So keep that in mind.
In order to determine any troubleshooting problems. So that's what's nice about that book. You can take that out in the field with you and use it as a guide to help you during your troubleshooting. After 15 minutes of runtime, you're going to check the actual temperature on the outside of the vapor tube right next to the service port on the large vapor line, and in this instance we read 55 degrees. So we take 55 degrees minus the saturated temperature we read on the low side gauge. So we're not necessarily using pressures to check the refrigerant charge, we're just using the pressure to convert to saturated temperature, and we're using the temperatures to check the refrigerant charge. So in this instance, we see that we have 39 degrees as a saturated temperature on that low side gauge. So we take 55 minus 39, and we're left with 16 degrees of total superheat. Total superheat is measured at the outdoor condensing unit, whereas a superheat measurement will be taken right on the vapor line right after the evaporator coil. But since there are no ports there, we check the total superheat at the outdoor condensing unit. So we take that 16 degrees of total superheat and we compare that to the 15 degrees of target superheat we measured earlier. The only change here is that we want to go back into the indoor unit and check the wet bulb temperature again, because maybe that has lowered by now. So now we go to the indoor wet bulb temperature, and we see that we're now reading 66 degrees as the indoor wet bulb temperature. And we're also now reading 90 degrees as the outdoor dry bulb temperature. So there was 2 degrees of a change on the outdoor dry bulb and 2 degrees at the indoor wet bulb temperature. So you constantly have to monitor those temperatures, because your target superheat is a moving number. It's not just a constant number or an average number like the subcooling rating is on the outdoor unit. So if our target superheat is 13 degrees and our actual superheat is 16 degrees, then that means we're just slightly undercharged. So we could add a little bit of refrigerant. It really would not be much, maybe literally a half an ounce or just a very small amount. But we're very close to what our target superheat needs to be, but we are 3 degrees off. If your actual total superheat is higher than your target superheat, then you need to add refrigerant. If your actual total superheat is lower than your target superheat, then you need to recover refrigerant. So you want to be within, say, 2 degrees of whatever your target superheat is at that point in time. So once again, you just got to remember that that is a moving number. You constantly have to be checking your indoor wet bulb temperature along with your dry bulb temperature.
I don't know why it exited out of there, but what I was going to say is he was talking about the superheat and the range there. Well, you can actually be plus or minus 3%. All right. So if you're within, let's just say our target superheat is 10 degrees, our range would actually be between 7 and 13. All right. So we want to make sure that, we understand that. We're not trying to get the exact number because it may be a little bit difficult. All right. We're dealing with a very finite amounts of refrigerant, changing conditions, that sort of thing. So if we're within those parameters, we're going to be okay. All right.
If your actual total superheat is higher than your target superheat, then you need to add refrigerant. If your actual total superheat is lower than your target superheat, then you need to recover refrigerant. So you want to be within, say, 2 degrees of whatever your target superheat is at that point in time. So once again, you just got to remember that that is a moving number. You constantly have to be checking your indoor wet bulb temperature along with your dry bulb temperature in order to put it on a chart, on an app, or also just be reading it on your digital manifold gauge set in order to determine what your target superheat is at that point in time. Before adding any refrigerant, make sure that you are purging the air out of the hoses before connecting to the refrigerant bottle. And remember that if you're really low in refrigerant, then you really wouldn't want to add refrigerant into that system. You really want to find the leak first, because what's going to happen is that refrigerant will just leak right back out again, and that's no good for the environment, and it's not good for the customer because they're going to get upset again. You really want to find that leak. You want to start looking for the leak with anti-corrosive bubble leak detector and maybe either an ultrasonic leak detector or a heated diode leak detector or something like that. But if you're just a little low on refrigerant, that may have escaped out of the Schrader valve, or maybe that was just from the service company checking the refrigerant charge each year. Every time you check the refrigerant charge, you are accidentally pulling a little bit of refrigerant out of the system. So that's a possibility as well. But this system would still work properly, only being 3 degrees off from what the target superheat would be. You're really looking for what's called a delta T of 18 to 21 degrees across the evaporator coil. And the issue with that is you may not be able to get an 18 to 21 degree delta T across the evaporator coil when you have a piston or capillary tube as the metering device when the indoor heat is high. So you have a high heat load such as the high indoor wet bulb temperature. If it's really humid inside the building, you may only be getting a 15, 16 degree delta T across that coil.
So what does he mean by delta T? All right, delta T is actually the temperature difference between 2 points. So we have our furnace over here, all right. Our incoming air will just come up from the bottom, all right, going to go upwards. And we'll have, let's just say, 70 degrees, all right. Our 70 degree temperature coming in, it's going to come up through the evaporator, and eventually it's going to come out through the top, all right. What we should see is about a 20 degree difference. So the air leaving the evaporator is going to be 50 degrees. That's what they mean by delta T, all right? The difference between our incoming return air versus our outgoing supply air is going to give us what our delta T is. If our system is not operating properly, without even hooking your gauges up, you can measure the delta T and see if your system is running like it's supposed to. All right. If it's got that 20-degree difference, hey, your system's running really good. I don't have to take the potential of hooking up my gauges or anything like that. If I only have 10 degrees, 5 degrees, well, then there's something wrong. All right. What's wrong? Well, it could be a number of different issues, but that's one of the simplest tests we can do.
But once the indoor wellpool temperature lowers, then you're going to be able to get that 18 to 21 degrees. You just got to remember that the piston cannot add more refrigerant into that system when you have a high heat load in the house like a TXV would. But if you do measure 18 to 21 degrees inside the building, it's just a confirmation that everything is good. Now, you should also check that high side gauge anytime you're checking the refrigerant charge, because if you have a very high subcooling, that could be an indication of a liquid line restriction problem. So say you had a saturated temperature on the red high side gauge of 135 degrees, and you were reading, say, 80 degrees as the actual temperature on the small liquid line, that would mean that your subcooling is 55 degrees, because subcooling is saturated temperature on the red high side gauge minus the actual temperature on the small liquid line. So if you have a very high subcooling, like 55 degrees or something like that, you may have that liquid line restriction problem. A liquid line restriction problem could be a clog at the filter dryer, it could be a clog in the screen prior to...
All right, I'm going to stop him right there because that's the next thing we're going to talk about. We're going to go ahead and we're going to talk about subcooling. All right. Subcooling is the amount of heat removed from a refrigerant after it has condensed, measured in degrees. So, yet again, remember, we've got our saturation point, all right? If we start to remove heat from that saturation point, the refrigerant's going to want to stay in that liquid state, and we're going to continue maintaining that liquid state, all right? So we're removing heat. Why is that important? Well, it's important because we want to make sure that we've removed as much heat out of our refrigerant as possible going through the condensing system, so that way we're properly going to send that refrigerant over to the metering device to be able to do its job. If we don't remove enough heat, well, guess what? We're going to have, let's go back to our analogy here, 122 degree PSI, 70 degrees. If I'm not at 60 degrees and I just maintain 70 degrees, well, guess what? Now I'm going to have that 70 degrees. It's going to hit the metering device. It's going to go through the evaporator. It's going to absorb another 10 degrees of superheat. It's going to go through. It's going to come back. And we're going to keep fighting this battle, all right? I'm never going to remove the heat out of the system like I'm supposed to, and my system is just going to constantly run and run and run and run. So we want to make sure that we're removing as much heat as possible, and in order to do so, we measure it via the subcooling, all right? The subcooling is used to properly charge a system with the TXV. Remember on the last slide when we were talking about that TXV constantly opening and closing? It's hard to measure superheat because there's a mechanical device constantly changing and altering it based on how much heat is being absorbed through the evaporator. So we want to come back on the liquid side line, measure our subcooling there, and we'll be able to properly give that TXV enough refrigerant to do its job. All right. So back to the same diagram that we had earlier. All right, it's very similar. All right, we've got the outdoor coil, and what's happening is it's going to remove, all right, all that heat because we've got cold air being blown across the coil. And you're going to say, well, cold air, it's 95 degrees. Right. 95 degrees is actually much cooler than, say, the 120 degrees that the temperature is here. So any type of cold air, or even warm air for that matter of fact, is going to be cooler than the refrigerant line, and so the heat is going to want to absorb into the ambient air, and we're going to go ahead, we're going to lower the temperature of our refrigerant. It's going to come back from a not superheated, but it's going to go from a high pressure vapor, and then it's going to turn back into a liquid. All right, that's why the condenser is called a condenser, because it actually causes the refrigerant to cool off and condense, all right, meeting back to its saturation point. So the subcooling calculation, real simple. What we're doing is we're actually going to measure the difference, all right, between our pressure and then the temperature that we're getting a reading from. So based on my gauges, all right, I've got 135 psig for 134A. I should have a saturation point of 105. All right, so as I move through the system, all right, my refrigerant gets cooler and cooler and cooler and cooler and cooler until it gets to the point where, hey, I'm measuring it right here, and guess what? Now it's 95 degrees. So I've removed 10 degrees, or I'm 10 degrees lower than my saturation point. So I've got a little bit of a barrier here before it's going to turn back into that saturated vapor.
Hey guys, this is Craig Migliaccio with AC Service Tech. Today what we're going over is how to check the refrigerant charge of an air conditioning system when the subcooling rating is not posted on the outdoor unit. Check out our book, The Refrigerant Charging and Service Procedures for Air Conditioning book. We have a full outline and sample pages posted over on the website, acservicetech.com. The subcooling method is the method used to check the refrigerant charge with systems that have a TXV. So that is measured on the high side gauge and the high side port. Air conditioning systems that have a fixed orifice, such as a piston chamber with a piston inside, use the total superheat method measured on the low side gauge and using the low side port. In order to determine the target superheat, we would need a target superheat chart or an app in order to determine what target superheat we need, and that's going to depend on the indoor wet bulb and the outdoor dry bulb. This is actually page 75 of the Refrigerant Charging and Service Procedures for Air Conditioning book. To check for the target subcooling, typically you're going to find that on the reading plate. This outdoor unit reading plate says the indoor TXV subcooling of 10 degrees. But some outdoor unit reading plates don't have a target subcooling and some are worn off. Some reading plates are completely sun-bleached and you can't see the target subcooling on them. Some outdoor units don't even have the target subcooling posted on the reading plate. So now I'm going to check the refrigerant charge of this R22 outdoor unit, and we're going to let this system run for about 5 to 10 minutes before checking the TXV subcooling. And the thing is, we want to make sure during that 5 to 10 minutes that our R22 saturated temperature is above 32 degrees. Now right here we're reading T1 and this is T1, so that's on the vapor line right here. So I'm just going to go ahead and press T2 and now we'll be on the liquid line measuring the temperature here. If we were to take a measurement of the subcooling right now, on the high side we're reading 98 degrees, so 98 minus 86, and we have about 12 degrees of subcooling. But obviously these are going to move around. If you notice over here, you see the saturated temperature is far above 32 degrees. So it's at 50 degrees, and that's because we're just turning this unit on for the first time, and the indoor wet bulb temperature is very high. When that indoor heat load is high, your saturated temperature and your pressure on your vapor side will be a little higher. So now we're checking the subcooling, and we see that we have 99 degrees as a saturated temperature, 99 minus 82, and you see that we have 17 degrees of subcooling. The target subcooling is typically going to be around 8 to 12 degrees, but I have seen some reading plates read 19 degrees of subcooling. I have seen some that read 7.9 or 8. So the thing is, the majority of the outdoor units say 8 to 12 degrees of subcooling. So if we looked at the target subcooling of 11 degrees, just so you know, the refrigerant charge is correct as long as we are within 3 degrees plus or minus of 11. So if you take 11 minus 3, you're at 8 degrees. So that's the lowest subcooling that these units typically have on the reading plate. If you take 11 plus 3, then that equals 14 degrees of subcooling. So anywhere around there is going to be the correct subcooling. So when the rating plate is wore off, I typically set the unit at 11 degrees of subcooling because that is very close to the normal range of most outdoor air conditioning units. So as you can see with this unit, we have 17 degrees of subcooling, so that's more subcooling than we need, which means that we need to recover some refrigerant out of this unit. If you want to learn more about checking the refrigerant charge, recovery, vacuum procedures, the pump down, troubleshooting the refrigerant charge, I have that all in this book right here. So I have the link to that down in the description section below.
So anyways, there's a subcooling example right there. He actually went ahead and he found an issue where the subcooling was too high. So the charge was off, so he was going to actually recover. He's going to remove some of that refrigerant to dial the system in. It may not be uncommon. You get somebody out there that doesn't know what they're doing, and they decide that, hey, we're going to pump up the system full of refrigerant, and they overshoot it. Sometimes things happen, the system starts operating a little bit differently, things get plugged up, so there's maybe the condenser is actually dirty, all right, and so now we're not removing heat, and so now all of a sudden we're getting a greater subcooling effect. So there could be various reasons, but you want to make sure that your air filters are clean, you want to make sure your condenser coils are clean, everything's operating like they're supposed to, there's no blockages. One big thing too is the airflow. We want to make sure that all the registers are open throughout the house, all right? People have a tendency to put stuff on there, close them off, thinking that, hey, you know what, I'm trying to direct airflow to somewhere else. Well, you do that too much, you're going to have issues. I had one customer, he's like, hey, my system keeps freezing up. I'm like, okay. So I head out there, and it's a brand new system, it's about 2 years old. He shouldn't really be having issues with it, but he is. And I'm like, well, so what's going on? And he's just like, I had it in here installed, everything was working fine, and all of a sudden my system seems to be icing up. I checked the pressures and everything is good. Everything from the from the outdoor perspective was great. So I go inside, checked his air filter, everything's clean. And I come to realize he's only got one return air grill for the entire home. And what he did was he actually blocked it with a massive fish tank. And by doing so, now there's not enough air coming back to keep that evaporator nice and warm, all right? Because what we're trying to do is we're trying to remove heat. Well, now that air was coming in from the basement, all right? That air is already pre-cooled in the basement, and it just kept on working and working and just getting colder and colder and colder until it got to the point where it just iced over. And so I told him, hey, you have to move that fish tank. It was probably a 100-gallon fish tank, 200-gallon fish tank, whatever it was. Sorry, I wasn't the one that put it there, but you're going to have to move it to make sure that it operates properly. So these are just some of the things that you're going to come out there, you're going to see in the field when you get into messing around with subcooling and superheat. So that's it for today, guys.